Alright, this is section 15.6. So following along from 15.5, which was surface integrals of functions, this is on surface integrals of vector fields. So before I sort of talk about what integral this is, like what it could measure, how we could evaluate it, we need a new concept. So let's say new concept. So let me explain sort of briefly why, and then when we explain the integral, it'll make sense. We'll explain why, and then explain the concept, and then we'll talk about the integral, and then that'll make sense. So when we're integrating over a curve, right, we have two kinds of integrals over a curve, right? So integrals over, let's say, a curve C, have two types that we've seen. There's the integral over C of a function, and there's the integral over C of a vector field. Now, for each of these, we have a curve, but in the second case, the curve needs to be oriented. In the first case, it doesn't. So in this case, C does not need, if you prefer, a direction. Officially, it's called an orientation, which we'll see soon, but just think direction if you like. For this one, C does need a direction. All right, so in the first one, the classic thing we were measuring is mass, and it doesn't matter which way you parameterize the curve. In the second one, we were measuring work, in which case it matters, right? So in this case, we were thinking mass. There are other things it could represent, but in this one, we were thinking work done by the vector field on the object. So the direction matters. So now we're looking at surface integrals. Right, so then we had the surface integral of a function. And we just had a surface. There was no sense of a direction or orientation or anything like that. Had no direction, whatever that means. We have no sense of that yet. We're about to. But when we do surface integrals of vector fields, we will. So for surface integrals of vector fields, let's say we'll need some sense of direction. Whatever that means. This is sort of what we need to define. So the official term is an orientation. So this is what we say. We say that a surface sigma is oriented basically if we've chosen a direction through the surface. So let's say if a direction through the surface. There's a sort of a more formal definition, which I'll give in a second. But this is like a good way to think about it. So here are a few examples visually. So if I have something like a plane, like horizontal plane, right? This is not oriented. Now, I could take that same plane and I could give it two possible orientations, right, which I'm going to indicate with, say, a green arrow. I'm going to say that one is oriented up. This one is oriented down. In each case, I'm sort of passing through. This is oriented up. This is oriented down. So here's another example. If I had, say, a cylinder. This is a hollow cylinder. This is not oriented. Now I could take that same cylinder, and again, I need to choose a direction through the surface. So you imagine on one side of the cylinder, like the inside, and you want to go to the outside. You're on the outside, and you want to go to the inside. So you could have an orientation that goes out, or you can have an orientation that goes in. So think of these arrows inside the cylinder pointing inside. So in the first case, we're oriented out. In the second case, we're oriented in. So the first one is not oriented, the second two are both oriented. And then, for example, you could have something like a parabolic sheet. So I'll draw 3 of these because we'll need 3 for the demonstration. This one, first one is not oriented. So I say, well, how could we orient this? Well, we could sort of, if you like, go to the right. It's sort of to the right and forward a little bit. Or we could go, this is going to be hard to draw, back and on the inside like this. So in the second picture, are we oriented, let's say, to the right? If you prefer, you could say out. We're just using loose descriptions here, and here we're oriented left, or if you prefer, in. So in order to define the surface integral of a vector field, I'll need an oriented surface, right? Now, just for those of you that are interested, here's sort of the official definition. So an oriented surface, so basically is a surface. So let me say this and then I'll write it. It's a surface along with a continuous choice of normal vectors at every point. Now let's say unit to be official, normal vectors at each point. So here's a picture of like an official example. If I had something like a hemisphere, in order to orient it, I would need to go to every single point on the entire hemisphere and choose a normal vector. And I would need to be continuous in the sense that I couldn't have another one right next to it pointing in. They sort of have to flow smoothly around. Now, of course, there are infinitely many of these. Looks a bit like a slightly startled hedgehog. But what we get here is we have all these little normal vectors all pointing out in this particular example. That's officially an oriented surface, right? This is officially, you know, we have a unit vector, we have a unit normal at each point. So sort of the official definition. But when we describe it, we'll use things like oriented up, oriented down, oriented in, out, left, right, forward, backwards, depending on how we've described the surface. So there are a variety of ways that we could do this. So now that we know what an oriented surface is, now we can define, we can sort of talk about what we might measure with the surface integral of a vector field. And then we can talk about how we might evaluate this thing. So here's sort of our definition / notation / concept. Just sort of, I want to talk about what we could possibly be measuring. So this is what I want us to think about. Imagine in three-dimensional space, this makes much more sense because we have a surface. Three-dimensional space, imagine it's filled with a vector field. And the vector field is giving like the flow of a fluid. Right? So let's suppose that F, the vector field in 3D, gives the flow of a fluid. So you can imagine, for example, I'm going to do these vectors in blue. Maybe they're flowing like this. And sort of picture this in 3D. It doesn't need to be a fancy picture in your mind. And so then what I'm going to do is I'm going to say, like, suppose that there's a surface, an oriented surface embedded in this, or sort of hanging in space. So let's do that. I'll do that in this picture in, say, black. So picture like a surface like this. That's our sigma. That'll be our sigma. And now it's oriented, so it has an orientation. So maybe the surface itself has an orientation, let's say, to the right. Right. So in this case, it happens to match the the vector field, but that's not really relevant for the discussion. So the vector field is F, that's in blue. So we can ask a really simple question. What's the rate of flow of the fluid through the surface in the direction that we've chosen? So in other words, what is the rate of flow? Now this, by the way, this is not sort of, when I say rate, this is awkward. There's no time in here. It's sort of rate per unit area, if you like, or total rate overall. So what is the rate of flow of fluid through the surface in the direction of sigma? In other words, in the direction of the orientation of sigma. Now, just to clarify, like, even though, so I say rate, and so just to clarify that there is really a time variable built in here. And so I just sort of want to not be overly confusing because I don't want to dwell too much on units. But there's a time variable built into the, if we're thinking of F as giving the flow of a fluid, there's a built-in time variable there. And so here we're getting a time variable that carries over. So, you know, sort of deep in the mechanics of it all, there is sort of a per unit time going on. Now, there are other ways that you could look about this. You could think about this as an electric field. You could think about, these are also called flux integrals, same thing. But the reason I like giving this flow of a fluid example is it makes sense to us. We can sort of visualize what's going on here. So in any case, the notation for the answer is that this is represented by the surface integral of F bar over sigma. And this is denoted as, so it's the surface integral over sigma of F dot n ds. Now, just a comment, this notation is a bit odd at first glance because it's not clear exactly what the n is doing there. So the n is really there sort of indicating these green vectors on the right. It's sort of, that's sort of addressing the orientation of the surface. Now that's a bit confusing, and you sort of in some sense don't need to worry about that because the method of evaluation will sort of take care of all the mechanics. But this is really what's going on here. So officially here, this, just so that you know, for those of you interested, this is really the unit normal at each point. That's sort of the green vectors that were over here. But again, don't worry overly much about that. It's not going to be such a big deal for us because the mechanics of evaluating will just take care of this. So then the question becomes like, all right, how do we do this? Right? So it turns out for us, there'll be two different ways of doing this, but it'll be pretty clear which approach we take. And we'll see that, you know, we'll talk about the basic approach here, and then the other approach will come in 15.8. So 3, evaluation, basic method. So there's one issue that comes up here, and here's the deal, is when we did the line integral of a vector field, the curve had to be oriented. So when we parameterize the curve, so this basic method is going to be parameterization of sigma. So in the case with a curve, we have to parameterize the curve to get the correct orientation. Right? Now, we don't really have a sense of how to parameterize a surface so that we have the chosen orientation of the surface. Like, this is a brand new concept for us and can actually make things a bit tricky. So instead, what we're going to do is we're going to have the basic method, and there's going to be a choice of plus or minus that comes up. So much like with the orientation of a curve, if you have the wrong direction, you might have to negate the integral, right? You might get the negative of what you expect. So same deal here, and then we can just have a plus or minus choice that needs to be made, right? So in any case, this is what we've got. Right? So suppose we want to evaluate this. Right? This is what we do. We're going to parameterize sigma. This is just in a sense like what we did in 15.5. We parameterize sigma by, we're going to have an R of u and v. This is x of uv I plus y of uv j plus z of uv k. This is with u and v restricted. Let's say by a region R in the UV plane, although typically this will be by inequalities. Like we sometimes won't need a picture. So this is what happens. This integral, right? So this integral that we're kind of trying to find here, this f bar, just for reference, really has an xyz in it. This is a vector field in three-dimensional space. So this becomes plus or minus. Now, I'm going to say something about this plus or minus in a second, but we'll come back to that. The integral over R of f. So everywhere I see an x, I put x of u and v. Everywhere I see a y, I put y of u and v. Where I see a z, I put a z of u and v. And then what I do is I dot this by the cross product of ru cross rv. And this is dA. Now, a couple things about this. When you do this giant mess here, this should all be in terms of u and v, whatever those are, right? So they could be x and y, depending on how we've parameterized the surface. This would be all u and v. So the result is just a simple, quote unquote, double integral. Now, I just want to mention this guy, this plus or minus. So plus or minus, typically the way we're used to it, means it's either, right? In this case, it's not either. It's one of the two, and we need to make a choice. So the way this works is as follows. We're going to use plus if ru cross rv matches sigma's orientation. We're going to use minus if ru cross rv opposes sigma's orientation. Now, it might not be clear exactly what I mean by that, and sometimes people find this a bit confusing, so we have to flesh that out in some examples. But the one thing I want you to note is it's just a plus or minus. It's not the end of the world if you make a mistake, right? It doesn't influence the overall value of the integral other than the plus or minus. So it's sort of a secondary small point. Like, it's important in a real world setting, of course, but it's not like a tragic thing that's going to affect how you integrate or anything like that. It's just a plus or a minus. So what we'll do is we'll work out some examples from start to finish, and so we can see how this all plays out. So for a few examples. So we'll say, first example, we'll say sigma is the part of the plane, let's say 3x plus 2y plus z equals 6 in the first octant. Oriented upwards. I'm going to put upwards in quotes just for a reason you'll see in a second. And let's find the surface integral over sigma of, say, xyi plus yj plus xzk dot n ds. So we're trying to find the flow of that fluid through that surface. And really I'm going to boil this down to just a double integral, because from then it's just grunt work. So, and we don't need to draw the vector field, but here's a picture of sigma, which will help. So we're in the first octant. This is a plane. It's one of those planes that we draw a little triangle for. So it has an x-intercept at 2. Let me do this in a different color. Let's do purple. So x-intercept is at 2, y-intercept is at 3, and x-intercept is up at 6. This is not really drawn to scale, that's okay. So it's this triangle, and the oriented upwards is sort of maybe up and out is a better idea here. So this is perpendicular to the surface, we're thinking about it. So that's our orientation. So upwards is a sort of a bit of a misnomer. It's sort of up and out, up and right, up and forward. But it's obviously different from the opposite direction, would be sort of in and downwards, right? Those are the two possible orientations. Right? So what we need to do then, according to the rules, we need to parameterize sigma. So for this particular sigma, the x and y are nice. They're restricted by a triangle. And we know what z is in terms of x. Right? So to do this, we note x and y restricted by a triangle. I'll draw that triangle in a second. And we know z in terms of x and y, because we can solve for it. So this is what we can do. We'll do r of x and y. We'll do xi, yj. And now we're going to take the plane and I'm going to solve for z. Alright, so that guy right there, this comes from right there, solving there. And in this case, we'll say, this is, we have x and y are restricted by, so I'll give this as inequalities in a second, but without inequalities, I'll do this in red. So just to actually be clear, let me go back up to this picture and indicate something. This was out, I got sloppy with my labeling, 3, and this was up at 6. So x and y are restricted by this triangle, where this is at 2, this is at 3, and if it helps, this triangle up here is this triangle. So if we wrote those as inequalities, we would have x between 0 and 2, and y is a bit trickier because they're not constants, like it's not 0 to 3, because that would give us a rectangle. So y has to go from 0 to the line that's on top, right? So this is a line which has y-intercept of 3 and slope equal to -3/2. This is 3 minus 3/2 x. So think of that as a vertically simple region, if you like. Those two guys describe that. So take a second to make sure that makes sense, because this is everything, right? Like the really hard work we've done now, right? So what I need to do next is I need to plug all of this into the formula, figure out what's going with a plus or minus, and then I have an integral, right? So before I erase the right hand side, notice what we need to do. Let me label some stuff here. What we're going to do over here is we're going to find this cross product, which means we need the partial derivatives. So we'll do that. And then we check this plus or minus. We plug all of our things into our f, and then we get a nice double integral. So let's do that. All right, so next, we're going to take the r, we're going to find our partials. So those will be r sub x and r sub y. This is 1i, these are the partials of the parameterization. 0j minus 3k. R sub y is 0i plus 1j minus 2k. Take the cross product. This is a particularly nice example because these are all constants. So it's a good example to start with. That won't often be the case. So when we take this cross product for the I component, I get 0 times -2 minus 1 times -3, so that's a plus 3i. I get 1 times -2 minus 0, so it's a -2, so plus 2j, and a plus 1k. Now, here's where we can make a note, right? So take a look at this guy. I'm going to mark this in green so we see. These guys, these vectors, these also point up and out, right? We can see that the z coordinate is positive, is a good thing to look at. Or the z, maybe the k component is better to say. k part is positive. So the thing is that these vectors match sigma. Let's say match sigma's orientation. If you look back here, you can see that those vectors over on the left point up and out, and this cross product points up and out. So what that tells us is we'll use plus. So then what happens next is the integral that we're looking for. So I'm just recopying this original integral right here. This becomes plus the integral over our r. So I didn't label the r per se. This is the r right here. You could also think about this as the r. However you like, doesn't matter. And so now comes the icky bit. Whenever I see an x, I'm sort of substituting in here. So whenever I see an x, I put in the I component of r, which is also x. Wherever I see a y, I put in the j component of r, which is also a y. So everything looks good, like nothing changes much. But now I see a z and I put in this. All right, so what happened in here is, let me use a different color, let's do pink, is this z became this using this guy over here. And technically, x became x using this guy right here, and y became y using this guy right here, but you know, those don't really change. And this all gets started with this cross product up here that we just calculated. So then, finally, I'll leave the plus. We could get rid of it, but it's good for now. When I look at r, we have inequalities for that. I have to put the 0 to 2 on the outside because constants have to be on the outside. Then I have 0, 3 minus 3 halves x. Then I'm going to dot these two. So I have 3xy plus 2y plus x. 6 minus 3x minus 2y dy dx. That comes from the dot product just above it. And then we just evaluate. This is a fairly straightforward, a bit lengthy double integral, but you know, not bad to do. So if you look at this overall pattern, I'll do another problem, but it'll be sort of the same thing as we have a vector field we need to integrate. I'll draw a picture of sigma because the picture helps us see the orientation, really, that's the thing. And then we'll parameterize the surface, find the cross products, check the orientation matching, plug into the solution. So let me clear the screen and then I'll do another example. So let's say, let sigma be the part of y equals 9 minus x squared. This is a parabolic sheet having, say, y greater than or equal to 0 and between z equals 0 and z equals 5, oriented to the left. Again, I'll put that in quotes because it's not exactly going to be left. That's just to help us see. And we'll find the integral over sigma. And let's do something really easy. X, y, z, I plus 2j plus xk dot n ds. So here's a picture of sigma. So if it helps, we know what y equals 9 minus x squared looks like in 2D. That can help us with the parabolic sheet. look like that. So in 3D, we get, so the curve that we just drew, like this curve, this little tiny picture, this will look like this. And we're between z equals 0 and z equals 5. So it's that surface, that's our sigma. And this is oriented to the left. So what I mean by that, this is sort of to the left and in, if you like, is maybe a better word. Maybe I have an arrow that's like sort of hiding in there. That's our orientation. If you had a top view, this might be a little bit clearer, but that's our chosen direction. That's our chosen orientation. And so again, let me just clarify those green arrows. Let me label those. Green is sigma's orientation is to the left. If you prefer, you could use the word in. Either one is fine. Whatever sort of makes you understand that we've chosen a direction through sigma going that way. Right? So how do we do this? Well, we parameterize sigma. So in this case, it's good to have a variable z because it goes from 0 to 5, and we know what y is in terms of x. So let's use x and z. So x will be x, y will be 9 minus x squared, because when we're on the surface, that's what we have. And we have z, which will be itself. And then we'll have x between 0 and 3. Oh, sorry, x between negative 3 and 3. And z between 0 and 5. So the parameterization of this one is actually a little easier maybe than the one before. Now just to clarify, just so we have a letter, this set of inequalities is our R. We could draw this in the xz plane, but in this case the picture doesn't really help. The inequalities sort of say more about what's going on. Then we find our partials. So we go R sub x. This is 1i minus 2xj. Notice there's a variable in there, no big deal. Plus 0k. R sub z, sorry about that, is 0i plus 0j plus 1k. Take the cross product. So I get negative 2xi. We get minus 1j, and we get plus 0k. Now, if we look at these, there's no sense of up or down to check orientation, but we can notice, like if you look at the simplest value that's in here, this guy, those are to the left. Because that's sort of the way the y direction works. So again, coincidentally, I have two problems in a row that work this way, which is a lot unfortunate. But again, this matches sigma's orientation. So again, you can see that over here. Those are the same. So again, we're going to use plus. Thus, this thing that we want. So fill everything in, this becomes plus, which I'll put in just a reminder, the integral over our r that we have down there with the inequalities. So same deal, everywhere I see an x, a y, and a z, I replace the I, j, and k components of r. So x gets replaced by x, y gets replaced by 9 minus x squared, z gets replaced by z, that's just 2, x is x. This gets dotted with the cross product that we calculated up above. This is dA. And then, again, I'll leave the plus just as a reminder. Now we can put in the limits of integration. Because everybody is a constant, it doesn't matter whether we do x and then z or z and then x. So I'll sort of do x first because it's maybe alphabetical order, however you want to think about it. And then we dot these. So I get negative 2x squared, 9 minus x squared z from the first. We get negative 2 from the second. We get nothing from the third because it's x times 0. This is dz dx. And then we evaluate. So the thing that makes it a little bit different is the cross product has a variable in it, but that never really came up. It wasn't a big deal. We had to be a little more careful with orientations because the concept of left for an orientation was maybe a bit confusing. Otherwise, it was very similar to the previous one. So let me do one more that has sort of has totally different variables. So we can get away from x and y and z because those are maybe a little too common and familiar and easy. Let's do something like the following. Let's say suppose that sigma is the half cylinder x squared plus y squared equals 9 with, say, actually let me do the full cylinder. This will make it a little more interesting. A little sort of more challenging problem. With, say, z between 1 and doesn't matter 7, and we'll say oriented in, and we'll find the integral over sigma of, say, we'll do a really easy vector field xi plus xj plus xk, just because that's totally weird. So for a picture, so this is a really easy cylinder. It's vertical, it's radius 3, goes from 1 to 7. And this guy is oriented in, which means also a little arrows are pointing in to the cylinder, if you like. Remember, the cylinder is hollow. If you had a top view, it can sometimes help understand the orientation. The top view in this case is our chosen direction is inwards, like this, versus outwards, which would be a different orientation. So again, the green is sigma is oriented inwards. Again, I don't really need quotes around in because in really makes sense, but that's all right. No big deal. So we're going to parameterize it. And this is just to clarify, this is our solution. So I can't stick with x or y and z because I cannot solve for x in terms of y or y in terms of x because there are multiple solutions. But it's a cylinder, so we can use z. Z is still good, 1 to 7, and then maybe theta, right? Because we can have a nice angle. So we'll do theta and z. So for the x and y, I need a cylinder of radius 3. So we'll do 3 cosine theta and 3 sine theta. That gives us a circle, and then we'll do zk. And then we'll do with theta will go from 0 to 2 pi, and z will go from 1 to 7. Now, quick comment, you might wonder what happens if you did z comma theta instead of theta comma z. So I'll say before we go any further that it won't change the answer, but I'll make a further comment about it as we go. But for right now, if you're wondering if I had done z comma theta, because I'm about to do partials and take a cross product, and you might wonder what would happen with the pluses and minuses. So if you're not wondering that, don't worry. If you're wondering that, just sort of believe me that it'll work out, and we'll say more in a minute. So just to clarify, the R that we're dealing with, this is a set of inequalities. You could think about it in the theta z plane if you like, but it doesn't really help to draw that picture. So then we take our derivatives. So r theta is -3 sine theta I plus 3 cosine theta j and 0k. Rz is 0I plus 0j plus 1k. Cross those. So when I cross those, in the x direction I get 3 cosine theta, or in the rather I component if you like. For the j component we get minus a minus 3 sine theta. For the z component I get nothing. So at this point you might be a little concerned because like it's not clear whether these match or don't match sigma's orientation. Right. It's hard to see because there's like none of these things are constants. So what you can do in this case is we can pick a specific theta and z, and we can look at where we are on the cylinder, and we can look at what this cross product is, right? So let's pick a specific point. Doesn't matter which point. So let's say theta equals 0 and z equals 1. So if I look where I am on the cylinder, right, so when theta is 0, I get 3 cosine theta, I get 3i, I get no j's, and I get 1k. And let's look at the cross product. Like, which direction is this? So I get the cross product is 3 cosine, this is also 3i, this is 0j, this is 0k. So what this means is on the cylinder, right? So where are we and what's going on? Right? So let me use a different color for this. Is we're at the point 3, 0, 1. So this is 3 in the x direction, 0 in the y direction, 1 in the z direction. That is that point right here. Right, 3, 0, 1. That's what the parameterization tells us. This vector that we just calculated, this points in the x direction only. So it points this way. So what we've done here is we've looked at a specific example of the cross product. Like in the other two examples, we could look at that cross product, we'd be like, oh, it's always up, or it's always to the left, or it's always to the right, or whatever. In this case, it doesn't work so well. In this case, we have to look at a specific point and be like, at this point, it's pointing forward, and now we can look over at the orientation of sigma, and we can say, this particular vector, this r theta cross rz, this is against sigma's orientation. Because sigma's orientation is inwards. Right? If you look back over here, all those vectors are in. This vector, this blue vector, is out. So those are opposing one another. So here we're going to use minus. So again, if that's confusing, that can be left for last. You don't need to do it now, and it only influences a plus or minus, which on an exam is sort of fairly minor in terms of point values, right? So again, in the real world, it's important, of course, but you have time to think about it and hash it out. Here, plus or minus, it's not the end of the world. So what do we get? We get this integral that we're looking for, all these x's. This becomes negative integral over r. So everywhere I see an x, I'm going to put 3 cosine theta from the original r. That's everywhere here. And then we're going to dot this with the cross product that we just did. dA. And then negative, the theta and the z, doesn't matter which way we do these. So let's do theta on the outside, because that might be more traditional. And we dot these guys, so we get 9 cosine squared theta, and we get plus 9 sine theta, cosine theta, and then 0, and then d z d theta, and then we evaluate it. So this problem's officially done. I want to go back and mark it up a bit just to point out something for the of you that might be interested. If you're good, if this makes perfect sense, you don't need to mark this up, but I'm just going to do this so we can make an observation. So the observation I want to make is just like, what happens if you had listed these in reverse order? Like, what if you had done z theta? So then you would have reversed the order in which you did these two. You would have r z and r theta, and these would be backwards. You would have done r z cross r theta. Now, you might say, well, that's going to give me a negative answer, right? So yes, when you change the cross product order, this would negate. So then you go, doesn't that change things? But here's the thing. The cross product negates, so when you check the orientation over here, this would now match. So then when you come down here, two things happen in this integral. This negative vanishes because they match, but this cross product becomes the negative of what we have here. So those negatives sort of cancel each other out. And the answer is unchanged. So makes it significantly, makes it work out nicely, right? So it doesn't make a difference how you order your variables. You'll get the same integral at the end. You'll get the same value. So that is the end of that section.